This video is a direct continuation of the previous one, where we derived the differential equations to describe the mass and energy balance of our stir tank system. Today we'll be in Python, working on modeling the concentration and coolant temperature of our stir tank system over time, especially when we change the initial coolant temperature going into the system. As per usual, we're going to start by importing numpy. Again, numpy being, let's see, numpy as np. There we go. As always, numpy is the basis for all of our numerical work in Python because it's so useful with the way it lets us manipulate arrays. Next, we're going to look at from scipy dot integrate. There we go. We're going to import solve underscore IVP. Now, solve IVP allows us to, yeah, I know what it does. Thank you. Solve IVP allows us to take a differential equation that has everything but the differential on one side of the equation, on the right-hand side, and it allows us to solve them for the equation that makes that differential true. Of course, we're going to be using that to solve the two differential equations we worked on in the previous video, and having solved them, be able to model the concentration and coolant temperature over time of our tank system. Now, also to plot that change over time of concentration and coolant temperature, we're going to need to from plotly dot, no, not plotly, dot plotly dot subplot. We're going to import make underscore subplots. There we go. And then finally, for my own interest, we're going to import plotly.io as PIO, and then we're going to make PIO dot template dot default equal to plotly underscore dark. And that will make all of our graphs look nice and dark to match with our window background setting. So to start, what we're going to need to do is we're going to need to import all of the constants that we have for this simulation. Now there's a lot of them all here on this page, so we're going to start doing them one by one. So we're going to start with Q, which is 100 liters per minute. So I'm just going to type constants right here. We start with Q is equal to 100. We're going to say right here liters per minute. Next up, we have the concentration of A of the water that's flowing in. So we're going to call that CA, so concentration of A in. We're going to call that, it was 1, and that was in mole per liter, right there. Yep. Next is the temperature of the water that is going into the system that's carrying all that initial concentration of A. So that's 350 Kelvin. So we'll make T in, set that equal to 350, and we'll notate right here that it is in fact in Kelvin, 350 Kelvin. Up next is the volume of our tank, which is 100 liters, so V is equal to 100 period liters. I shouldn't say period, I should say decimal, but that's besides the point. Next is rho, which is our density of water, which is just 1,000 grams per liter. So rho is equal to 1,000. That's going to be in grams per liter. Next, we have C, which is our coolant heat exchange constant. I'm not exactly sure what I called it in my previous video. I think I called it C therm or something similar, but that's besides the point. What matters is that it's capital C here, and it's 0.239 joules per gram Kelvin. So capital C is equal to 0.239. 0.239, that was in joules per gram Kelvin. Joules per gram Kelvin. Yep, 239. So next is our heat of reaction, which I'm just going to call HR. This is the amount of energy put out every time 1 mole of reaction takes place. But since our reaction is the same as the concentration of A, because it's 1 to 1A turning into 1B, so it doesn't actually matter. But the fact is that each one of our reactions puts out, how much heat was it? Puts out 5 times 10 to the 4 joules per mole. So 5E4, and that's in joules per mole there. All right. Up next, we have E divided by R, which is used to calculate the rate of the reaction rate, which is based on the initial K0 right here below that reaction rate, how do I put this? The constant when you include the influence of temperature gives us our reaction rate. So that's what K0 and E over R. So I'm just going to call that ER, just call it ER, and that's equal to, it's going to be 8750 Kelvin. So 8750 Kelvin. Oh, I need to make sure Kelvin's in. 8750, yep. Okay, K naught is going to be 7.2 times 10 to the 10. So K0 is going to be equal to 7.2 E10, right, 10 to the 10. That's going to be in, I'm going to call it HC because it's, I guess it's not hertz, it's min to the negative 1. I almost abbreviated that as hertz, but that's cycles per second, not actually per minute. So good thing I caught that. And then finally, our UA, which is another one of our, oh, I just realized capital C is not the coolant, it is the heat capacity of water. That's my bad, my mistake. Capital C is the the heat capacity of water. UA is the joules per minute Kelvin, which is the thermal sucking, I suppose, of the coolant. So UA is the one that corresponds with the coolant. I always get those confused because they both have to do with joules, but yeah, joules per gram Kelvin is heat capacity because that's how much heat the ratio between energy in joules and temperature and heat for every gram that is being heated, compared to this, which is joules in Kelvin per minute, which tells us how much energy it's sucking out, and then corresponding that to the temperature that is being decreased, and then over time. So that was my mistake, but I'm glad I caught that now. It was just a nomenclature thing, but it's still very important to know. So next is UA, which is 5 times 10 to the 4. So we have 5E4, right? 5 times 10 to the 4, and that's going to be in joules per minute Kelvin. Finally, down here we have our 3 initial conditions. Now, for the sake of what we're simulating, in which case it's when we change the coolant temperature from 300 Kelvin, which is what it says down here, to 290, or when we change it from 300 up to 305, since at time 0 is the instant that switch happens, we're not going to need to include TC directly because we're going to be using our TC. There's no, essentially, these changes to TC become TC0 because that's the moment we start recording our graph will be the moment that it changes the temperature of that coolant. So we're not going to write 300 Kelvin down, but it's good to know that that's technically what's happening at, I guess, if you would say a negative time, because time previous to 0 at the point where we switch the temperature of the coolant. So we're going to start right with the concentration of A0. So we're going to call these initial conditions, initial con, and we're going to say CA0, CA0 is going to be equal to 0.5, I believe. 0.5 moles per liter. And also we're going to need 350 Kelvin for the T0. So T0 is going to be equal to 350, and that's in Kelvin. So now we have all of our initial conditions and our constants for this simulation set up. So now it just comes down to actually working out the differential equations in Python that we wrote earlier. Then it's going to be plugging those into solve IVP, turning that into a plot based off time, and then plotting that in Plotly. So we'll just mark these. Everything seems good. If there's an issue, we'll find it when our graphs look really wonky, but hopefully they look correct, and that will mean we're doing everything correctly. So now we're going to define a function we're just going to call diff eq. And as we remember with solve IVP, which is what we're using to solve these equations, what matters is for whatever function that we reference in that we want to be solved, we have to make sure that time is always the first thing that we're importing, and second is going to be the vector of the 2, I guess, equations that we're going to be solving. So immediately we're just going to unpack to be concentration of A, and what's the other one? TC, the temperature of our coolant, is going to be equal to our vector that we're importing. We're going to immediately unpack it. And now all we're going to do is we're going to just simply return the values that we need that we calculated in our previous video. So I have that up on my second screen. In the video for you, it's going to fade in nice and slowly. Very nice. The handsome devil with his nice little hat and smile are going to be there. So what we're going to type is we're going to return, and we have to remember that what we're returning is actually going to be an array of the two different differential equations. So right away, we don't have to actually use parentheses. Now that I think about it, we can just put the array. Sometimes I put the parentheses and then the array within the parentheses, but that's not really necessary. Also, I hate the way it looks when it segments it like that. I much prefer it to look like this. So the first one we're going to look at is the simpler of the two, which is going to be the mass, the mass balance, where it says the change in the mass in the system, or the concentration of A, can only be what's leaving out A, what's coming in through the input, and also what's being transformed into B, and obviously they're, of course, being subtracted from our total as the reaction takes place. So looking at the equation that's starred right there, we're going to know that the left-hand side is the dCA over dt, the change in concentration of A over time, and that's going to be equal to the Q times V, so Q, we're gonna write it this way: Q times, and then we're gonna do the divide by V at the end, parentheses by change in. Oh, that's actually really low res, and I can't actually read what I wrote. CAN. There we go. So CAN minus CA. So that's the difference between what's coming in and what's going out, multiplied by the flow rate. So that's again our mass flow, the difference in mass flow, all divided by the volume of our tank, which I used lowercase v in this case. So that's what's coming in, right? The difference in what's coming in through the flow minus what's already in there, times Q divided by V, which gives us the total mass coming in from our input stream. And then we're also going to subtract the concentration of A that is leaving. Obviously, this minus CA is the amount that's leaving through the outstream. This is going to counter the amount that is being consumed in the reaction that's taking place in our container, which is going to be K, a reaction constant, which we haven't defined yet. That's why it's underlined, but we'll get around to it, multiplied by the concentration of A currently in the tank. Because again, since the reaction is taking place in the tank, obviously we're going to have to know what the reaction, the concentration of A in the tank is in order to figure out how much and how fast it's reacting. So I didn't want to do that. I wanted to just start typing here. So the next thing we're going to want to do is our second equation for our energy balance. And let me scoot my image right over here so I can see and type it correctly without having to worry about messing up the subscripts, because my eyes are bad, and I'm sure that's already been talked about for sure to death. So again, on the left side, we have the change in temperature over time, which is, again, the left hand. That's what we're solving for. We want to know how it changes over time and which equation in form of T will match the change in time that is predicted with the constants we've been given. So it's going to be the same thing as before with mass, but this time with the difference in temperature between what's flowing in and the actual temperature of the tank right now. So we're going to do Q times parentheses T in minus T, and that's going to be divided by the volume. Again, that's going to tell us this is going to account for the temperature, the energy that is being brought in by temperature, by the higher temperature flowing in, and the amount that's being lost as the well-mixed mixture in our tank at temperature T flows out. So again, that's going to do our ins and outs. And then we're also going to have to figure out the energy produced by the reaction. So all of that is going to have to probably be encased in parentheses. Or no, it's fine, because we're going to just add our the reaction energy generated. So it's going to be HR, which is again the amount of energy generated, since we've already negated it in Python instead of making it subtracting here because HR is negative. We just made HR the variable positive, our constant, so we don't have to worry about negating anything. So the amount of energy generated per mole of reaction times the moles of reactions taking place, which again would be the rate of reaction times the concentration. So it's going to be K times Ca, the concentration of A in the tank, divided by, and then in parentheses, we're going to divide that by the density, rho, and also by, oh, that's really hard to read, by the heat capacity of water, I believe. Yes, heat capacity of water. If that's correct, which I think it is, it's just, again, this photo is very, very, it's not as high quality as I would like. It's not low quality, but it's not as high quality as I would like. And I'd really like to be able to zoom in a bit more with my eyes, but I can't without getting really close to the camera and it making it very uncomfortable. So I'm trying my best to look. I'm pretty sure it is capital C, the heat capacity of water. Yes, capital C, heat capacity of water. So this is accounting for the energy that's coming in and out through our input and output streams. This is accounting for the energy generated as the reaction takes place. And then we have to subtract any energy stolen away by our coolant. So we're going to have UA, that's again our our conversion factor between joules of energy and temperature of coolant taking away, and that's going to be that's going to be the difference between the temperature of the tank and the coolant temperature, because that's the simplest, the Newtonian way of calculating heat transfer. It's the difference between the hot thing and the cold thing obviously being the coolant, and then UA just figuring out how to convert that amount of temperature difference into heat extracted. So that, and then that's going to be divided by the rho density of water. I'm going to make sure to put this in parentheses because I want to make sure. Rho times the volume of our tank times the heat capacity of water, once again, which is capital C. Wrap that all in parentheses. And we should see that everything is defined. Yes. Am I missing something? T is being highlighted, but T is the temperature of the tank, right? Why would it not be be? Oh, it's because I'm bringing TC in instead of T. Yeah, that's my mistake. So the mistake I made here is we want TC to be undefined right now because it's going to be later defined, because that's what we're changing. We haven't defined it up here. That's what I missed by not including TC here. I went to highlight it, instead grab the image. That was unfortunate. Instead of putting in TC here, we're going to be inputting TC right as we go to calculate it, because that's what's going to be variable between our two states of increasing it from 300 to 305 and decreasing it from 300 to 309. So TC is supposed to be undefined as of right now. We'll get around to that in a bit. The other thing we're going to want to do is we're going to want to define K, because as of right now, K is undefined. And if we look on the far left, it's not actually starred, but right next to our tank, you'll actually see the K equation that I wrote out, which you can see that K is going to be equal to K0, K naught, which again is our starting factor, multiplied by e to the power of negative the RE or ER factor, which is in degrees Kelvin, divided by the temperature of the tank. Because again, the temperature at which our reaction is taking place is going to affect how quickly that reaction goes. As temperature increases and the reaction gets hotter, it's going to begin to react faster, which of course, when you have a reaction generating heat, can sometimes cause a runaway reaction, which we'll actually see with one of our two coolant temperature cases. So anyway, in order to do exponentials with numpy, we're going to do np dot exp, and that's going to be the exponential of shift ER divided by the current temperature, and we're going to want to make sure to make that negative, because it's the exponent of the negative ER over T. So that should be everything. We'll define this, and everything's good. We're importing a vector with, again, two variables, the concentration of A and the temperature of the tank, and we're outputting, make sure we include the comma there, we're outputting the mass, which is the concentration of A, which the mass balance, which is equal to the concentration of A, and right here, the energy balance that is equal to the change in temperature of our tank. So now that we have that written, all we have to do is plop that into our solver and then graph it. So now, moving next is going to be, we're going to do our solve IVP. And remember, the first thing we're going to do whenever we do solve IVP is the function we want to solve, which is our diff equations, diff EQ. I want to make that diff EQS because we have two of them, so I'm going to make that there, make that here diff EQs. Next thing we need is our time span, which I'm just going to say is from 0 to t end, and we're going to have to define our t end up here, which is fine. T end is going to be equal to, we'll just say 10 for now. 10's a pretty good length. So t end, it'll be in, I'm assuming it'll be seconds, or will it be in minutes? I'm not totally sure. So we'll leave that blank for now, but we'll just go with 10. 10's a nice, good number. It'll be enough to give us a view of the cyclic nature of our tank changes. So from 0 to t end, that's fine. Next, we're going to need, actually, let me check this. Is this supposed to be a, I think it's, is this supposed to be a, I think this is supposed to be, it's not an array. T-span, I think T-span is supposed to be not an array, because it's supposed to be, T-array is supposed to, the T-end, from 0 to T-end is supposed to be a non-array. It's supposed to be a start and an end point. It's a point value almost. It's not actually an array of values. So after that, after we do our time in and time out, if it will go back to telling me what I have to do just to make sure that I get everything right. Y0 are our initial inputs. So we're obviously going to have our initial conditions. We're going to be Ca0, our initial concentration of A in our tank, and T0, our initial temperature of the tank, because that's what's going to plug into right there. And then we're going to unpack that, making sure we have the right order, Ca and T in that order. Yep. So our method, we're going to use method is going to be equal to, we're going to use the Radau method, R-A-D-A-U, which is just the preferred method. It's technically slower algebraically or mathematically, but we know that it gives us the best output. And when we're doing it on Google's computer, on Google's time, and on Google's gigabits and teraflops, not our problem if it's more computationally intensive, because Google will get it done either way. And the final thing we're going to do is enable dense output, which is instead of true. So instead of just enabling, what's the word that I'm looking for? Instead of just enabling dense output basically produces the actual function. It allows for the production of an actual function that matches the differential equations, in terms of t. So our y of t for these differential equations, as opposed to simply spitting out like, yep, they've been solved. So without dense output, we wouldn't be able to extrapolate that function for any length of time within Tn, like any subdivisions of points that it doesn't find particularly interesting, because that's how the Radau method uses it. It picks specific points and plots them and tests them, and that's how it comes up with the standard function which matches the differential equations. So again, still seeing this red right here, Tc, we're going to have to define Tc. So the first one we're going to do is the one where we lower the temperature from 300 to 290 Kelvin. So we're going to test through the 290 Kelvin first. And if we do this, we see it has successfully reached the end of the integration interval. We see that we have our success. Our solution is right here, this object at memory. So that's the one we care about. So we're going to do .sol, and it's going to just tell us that. So we're going to set this equal sol. So now we've assigned this the solution object in memory to the variable sol, and now we can use that from memory to graph according to whatever span of time we're actually interested in. So to do that, we're going to start our plotting now. We're going to make our time plot, which is going to be our x-axis, and that's going to be np.linspace from 0 to, we'll just do it to tn, so we'll just look at all of them, and we're going to do my favorite number for divisions, 501. So we're going to have 501 time points that we're going to plot from 0 to tn, which right now is 10. I don't remember if it's minutes or seconds. I think because this is in minutes right here, these are all in minutes, I'm going to assume that it's in minutes, so it's from 0 to 10 minutes. That's fine. So now that we have our t-plot, all we're going to do is we're going to solve, I guess we would call it CA plot, comma, and our T temperature plot from the solution that we generated for each of them of our time plot. So what this is saying is it says take our set of inputs, our array of inputs right here from 0 to tn, 501 points, run it through the solution, and because solution is the actual equations that correspond to these two differential equations, it'll run that array of inputs through both of these, and will spit out a bunch of output values for the concentration and a bunch of output values for the temperature. And obviously, we need to unpack those into each of their own respective plots, so then we can actually graph them. So the final thing we're going to do is we're going to figure 1 is equal to we just do make underscore subplots, because we've already imported it from Plotly. That's the one thing I almost always mess up. Make subplots. So then we're going to do fig1 dot add underscore scatter 2. That x is equal to, well, for both of them it's going to be t-plot, because this is our graph of time. Need y is equal to t underscore, we'll do concentration first, so we'll do ca underscore plot, and then we want it to be in a bunch of, we want the points to all be connected by a line, so we're going to leave the type of, like a, what do you call them, like markers, but we're going to leave it as lines because we don't want that to be affected. We're going to do that, and we want to have them side by side. now that I think about it, because that's the final output. It's really nice to have one right here and one right here so that you can see them both and see how they correspond to each other, especially as we change the temperature. So we're going to actually make this to be, we want them side by side, so that would be, we'd have 2 columns in a single row. So columns is going to be equal to 2, rows equal to 1. I think that would be good. So we're going to have this one set at, what's going to be, since they're both in row 1, they're just going to be equal to row is equal to 1. Column, I think it's just abbreviated to col, is equal to 1 because we want the concentration to be on the left. And then we want the name to be equal to concentration of A. And then basically we're going to do more or less the exact same thing for our time plot, except instead of being a plot, the output being the plot of concentration of A, we're just going to be plotting the change in temperature over time, and we're going to want to be in column 2 because we want it to be to the right of the concentration of A. And then this is going to be tank temperature. I think did I spell temperature right? Temperature. Okay, yes, that's spelled correctly. So I think this should graph our coolant at a temperature of 90, hopefully. Maybe it looks too smooth. I'm not sure. I'm not entirely certain, but I'm pretty sure this is right because I'm pretty sure it's stable. Yeah, this is good. This is good. I bit my tongue because I was a little foolish, but this is what it's supposed to look like, where we start at 0.5, and then as A decreases, or as the concentration of A increases, so does the rate of reaction, and as the rate of reaction increases, so does the it decreases the amount of A flowing out. So eventually it stabilizes up here around it looks like it stabilizes at 0.952. So 0.952, I believe our concentration of A was in moles per liter. So that's its stabilization. Now, just to double check that it's working, and again, to show you the other value, we're going to change the initial value of our coolant. So obviously when our coolant, from 300 Kelvin to 290 Kelvin, the coolant becomes colder, which means it's able to suck more heat out because there's a larger temperature differential between in the tank and outside the tank, which means it's more efficient at cooling, which helps stabilize the reaction. But if we turn it up from 300 to 305, rerun the solution, replot it, now we get some real janky cyclical stuff, because what happens is the concentration of A is up at 5, and what happens is as the reaction's going, it's producing more heat, more or less, than is actually able to be pumped out by the coolant. So obviously the tank's heating up. And as the tank heats up, that increases our K value for the reaction, which is the rate of the reaction. So as the rate of reaction speeds up, more A is spent. And as more A is spent, more heat is generated than is pulled out by our coolant, because our coolant's hotter at 305. So the difference between 305 and 350 in the tank is less, so there's less heat being pulled out, which starts burning more A, burning as in consuming A in the reaction that generates heat. And so it becomes a feedback until eventually we hit more or less, there's no A in the tank. And once it does that, since there's no heat being generated, all heat's lost, the temperature very quickly, right there when it hits 0, starts decreasing as the coolant begins to be semi-effective. But as it begins cooling, more A is allowed to accumulate, which kind of starts the reaction again, and of course it hits that, and it doesn't quite get to 0 before it basically stops being a runaway and it catches itself. But obviously it just keeps doing that forever, never stabilizing, and continually just being a real mess. And now when you think about the fact that this is in an enclosed container, or it could be in an enclosed container, it doesn't have to be, but in the case that it were, obviously suddenly hitting 440 degrees Kelvin, 440 Kelvin in your vessel is not going to be good, especially if the concentration of A and B you're working with are perhaps flammable, self-ignitable, they're oxidizers. I mean, who knows what could happen? It could overflow the tank as everything expands, as it gets hotter and hotter. It could, start pushing on the walls of your closed container if you're using one and cause an explosion or a rupture in a tank. So all in all, it's very much not a good thing to have this runaway reaction. So it's much, much preferred that we would decrease the coolant of our tank and get a nice stable reaction that settles out at 0.952 grams per mole of our concentration of A. So that's all I've got for us today. For Python, we've successfully marked our colder and our warmer versions of this tank problem and shown how one stabilizes and the other becomes cyclical and unstable and potentially dangerous or even fatal to workers nearby. And I mean, it definitely shows you that even a few degrees in coolant temperature can really make a difference in a system. So make sure to keep those coolant pressures low and also to have a great night. Thank you.